this one. That one, this one? Yes. That's it. Good afternoon, everyone. My name is Scott Zemerick, and I'm from the NASA IV&V program. And today, I'm going to talk about kind of two separate things. The first goal of this presentation is to give you an overview, a little bit of the NASA IV&V program, a little bit about what we do, and how the Independent Test Capability Team, ITC, fits into that. The second and third bullets there, I'm going to talk a little bit about some software-only simulation that we do, and finally, a specific example of a continuous integration build server for CFE and CFS. So a little about IV&V. We are the NASA IV&V program. We are technically independent, managerially independent, and financially independent. And IV&V does a risk-based assessment to pick which NASA projects they're going to look at and perform IV&V. I'm not going to go into a lot of detail about the IV&V analysis, but it's done on the full life cycle of the projects and the missions. But I'm not going to talk a whole lot about that. What I am going to talk about today is the ITC team, Independent Test Capability. We are a team, part of IV&V, and I put our charter up there, but what the charter really says is our team builds virtual test beds and software-only simulations for NASA's spacecraft. We build simulators that allow IV&V to do independent testing. That's what the ITC team does. On the right side, we have a laboratory that's called the JSTAR Laboratory, named after John McBride, the first, the only astronaut from West Virginia. The JSTAR Lab is our infrastructure for deploying our simulators. Just a little bit more about this. We use a cloud-based infrastructure. We utilize desktop and server virtualization, so IV&V practitioners can use our products that the ITC team develops. We maintain multiple strings of simulator deployments, both on-site at the IV&V facility and off-site at various NASA centers. We very often do an integration of COTS and GOTS software tools to support IV&V. I won't go into a whole lot of that, but we do a lot of that on SLS and MPCV projects. And I'll talk mostly about software only, but the last bullet there, hardware in the loop, we do occasionally use hardware to perform independent testing at the facility. Specifically, RAD 750s, 50-3, and Spacewire hardware. That's what we usually focus on. So throughout the course of our team, since 2009, we've developed a few spacecraft simulators, or also I'll refer to them as virtual platforms too. Simulation means a lot of things to a lot of different people. I think what we really develop are virtual platforms for doing testing. The first one was our prototype to see if this would actually work. We did a spacecraft simulator for GPM, Global Precipitation Measurement. We heard that mentioned today. It's already launched. And the purpose of this simulator was to test the unmodified flight software. That's what we focus on, testing the unmodified flight software. We do not change the flight software. We build our simulators, we build our virtual test beds, and we just get the flight software, we throw it in, we run it. And that allows the IV&V practitioners to do their independent testing. So we kind of enable them to do independent testing on a software-only simulator. The second project, we are currently working on a complete James Webb Telescope integrated simulation and test simulator, which we call GIST. This is kind of our flagship product. It is currently being used right now, and it's under active development. In the middle here, I mentioned NOS. We heard today about some common frameworks for developing flight software. We have a common framework that we use to develop our simulators, and we refer to that as NOS. I have some backup slides, and if anyone's interested, I can go into that. Essentially, NOS is a set of tools and a synchronous middleware that kind of drives and allows our simulators to do the work that they need to do. The last one was Discover. It's due to launch in January. It was a rather small mission, and we had a quick turnaround on. Upon releasing this simulator, a flight software bug was found, I believe, within hours of using our software-only simulator. So a little bit about software-only simulation. It is a complete software representation of modeled hardware components and software emulators. Together, this forms a full spacecraft simulator. What this means is our team, we usually go to the NASA centers and we find racks of hardware and we virtualize that and we turn that into software-only simulation so that we can execute the flight software on a typical server or a laptop without needing 1553 cards hardware, without needing spacewire hardware, without needing that underlying hardware. We just cut all that out and then we build a software-only simulation. Some of the advantages of software-only simulation is that it provides complete control of the CPU, the timing, the memory, and the peripheral devices. And this is where things get kind of fun because we can stop execution at any time. We can stop all threads of the flight software. We can peek memory. We can poke memory. We can perform fault injection very easily. We don't have to break hardware to do fault injection. We can simulate that with our simulator and inject any fault that you may be interested in. So the main use cases for the simulators are, namely, number one, IV&V independent testing. They are essentially the customers for the ITC team. We build the products that they use to perform independent testing. They drive what we do. Secondly, operator training. You can have a complete spacecraft simulator running on a laptop that you can put down in front of an operator, and they can exercise and run their ground scripts just as if the spacecraft was right in front of them. That's a use case that we're looking into right now and had some success with it. And the last one is augmenting project hardware testing. One contractor on a project could not perform testing of requirements. They could only do it through software inspection. We could actually fail the hardware in our virtual sim in ways that they couldn't do on the hardware. So that was able for them to perform some additional testing. So what are the components of one of our simulators? On the left, a typical CNDH system. A typical CNDH system has hardware, maybe a compact PCI chassis, spacewire, 1553, Ka band, S band, FPGAs, any that you will find on any typical spacecraft. We model that hardware. Then on the right side, over here, we have an instruction set simulator where we can use the example of a RAD 750 or PowerPC 750. We have that board, that processor modeled, and it will run the unmodified flight software binary. Taking that running with our modeled hardware, you now have a spacecraft CNDH system that is up and running the actual flight software binary. Then we couple that with the operational ground system. This could be ASSIST, this could be ITOS, this could be a ground station from Raytheon. We have experience in all of those, but regardless, we make the user interface for our simulator the operational ground system, the same as what the operators would be used to. So what are some of the use cases for this? For independent testing, a practitioner analyst might want to halt the entire system. They might want to look at memory analysis, fault injection. On the other hand, you might have an operator who's being trained on the system. They could run their different scenarios, and they can do their what-if scenarios. What if something fails? What if they need to do this? So this diagram here kind of shows the main components of one of our simulators. Back up for 1 second. I would like to point out that the instruction set simulator, we typically use our Zemerick, which is a Wind River product, and we also use QEMU. QEMU can be pronounced many different ways. I'm going to say QEMU, but you've probably heard it pronounced any number of ways. But it is, going to the next slide, it is a generic open source instruction set simulator. And this whole slide on chemos here is because we heavily used it for our CFE continuous integration system that I'll be describing in just a few more slides. Out of the box, Chemo already had support for many CPU platforms: x86, Spark, Coldfire, PowerPC. We have taken Chemo and kind of built on top of it with some of our own technologies. We have a Chemo RAD 750 model that you can run under Chemo. So any flight software that runs under RAD 750, there's a good chance we can run it under Chemo. And that's kind of what we're doing in this. I'll show you in just a second.
Are you pushing that upstream?
What do you mean?
Back into the
Back into?
source repository of Chemo.
We cannot for the RAD 750 because it is ITAR. Yes. Yep.
What for the MCP 750?
I think MCP 750 is already there. I think it's there.
Okay.
There is the PPC 750 is part of Chemo already. What we did was we modeled the RAD 750 board. So the CPU is in Chemo, but the board and the peripherals we modeled to then give you the actual board for the RAD, because RAD 750 is a specific board from BAE. So to that point, though, well, we have modeled Ethernet in Chemo, a very common Ethernet chip that's used on a lot of missions. We have that modeled. And we just got the 1553 compact PCI card Summit chipset, if you're familiar. It's a very common 1553 chipset. We have that modeled in Chemo as well. So you kind of see here, if you put a bunch of these pieces together, you kind of have a whole spacecraft that you can run under Chemo, and then throw in the flight software binary. You could have a system able to test all under an open source emulator. The last bullet there, Leon 3, we actually got some patches from ESA on Leon 3 to make Chemo work, and we were successful in that. And we or ESA are planning on pushing that upstream. I know the gentleman who worked at ESA, he just didn't have time to do it. And we said, well, give them to us, we'll take a look at it, and maybe we can push them upstream for you too, because there would be no issue with that at all. So that takes us into our CFE-CFS continuous integration system. This is a little bit different spin of the simulator topic that I've been talking about. But what we're looking to do here is provide an automated means to exercise build system tests for CFE. Our team chose CFE as a pilot project due to its size, its usage, its popularity. Some things are done manually right now, and it has dependence upon ground station software. But this project actually fits into IVNV in a bigger way. This is a pilot project, but the concepts here we want to provide to the IVNV program so they can infuse this into the way they do their analysis. And that'll become a little more evident as I go on. Build system tests. When I say build system tests, really mean those are integration tests that are made to test CFE using the ground station as the driver. That was the main focus of this effort. We're looking to do full-up automation of the ground system to build the test, run the test, execute the test, and then get the results of the test. We did not focus much on the unit tests for CFE. There are lots of them. It just wasn't a focus of this effort. One thing that we do is, with our work with Chemo, we can support multiple targets. So we're looking to execute tests in an automated fashion on multiple targets. Linux x86 or VxWorks running under Chemo, our RAD 750 model that I just mentioned previously. The outcome of this is that you could have a regression test suite for multiple targets where you just throw in new CFE software, hit a button, come back the next morning, and you have your results. And the last bullet, the purpose of this is so that we can apply this to other IVNV missions in the future. So replace CFE, CFS with Project X flight software. We get new flight software, throw it in this system, Ground station is your driver, as is often the case for some of these tests that the projects do. Hit the button. We support RAD 750. Come back the next morning, and you have your test waiting for you. So that's kind of the purpose of this project. That's kind of where we're going with it. So some of the technologies to put this system together, we've heard these mentioned a little bit already today. Atlassian is a commercial company, and Bamboo is the build server, and it's the first item listed here. It is the automated build and test. It's what does the building and what does the testing. The next is Assist. Assist is the ground station of choice for CFE, CFS. This could be replaced with ITOS. This could be replaced with any number of ground systems. We've seen many. Just so happens Assist is the one. So ITC developed a wrapper for Assist to automate it. We have the ability to start Assist, build procedures, and execute procedures. So that was some of the technology that ITC team developed for this effort. Likewise, we developed plugins for Bamboo, the build server. So this is a way for us to tell Bamboo how to build CFE. That's what the purpose of this plugin is. Obviously, we need the core flight system software. We utilized our QEMU RAD 750 model, and we utilized our Ethernet model also in QEMU. Little on the architecture. We deployed 2 virtual machines. So the pink box you see here is just consider that your host machine. And over here, if you work your way out, you'll see that start with CFS, work your way out to VxWorks kernel. That runs under QEMU, under a RAD 750 virtual machine. So that's kind of your system under test with CFE inside of it being executed. Over here, you see 2 more virtual machines. One of them is the ground station software, and the other one is Bamboo build server. On the next slide, I'm going to expand a little bit on the Bamboo build server. I'll show you another block diagram of it. But it's really the one that coordinates all the activities across the VMs. So you have 3 VMs in play here. You have the software under test running under QEMU. You have the ground station, and then you have the Bamboo running. That's kind of coordinating the effort between all of them. If we were to add other targets, then that's what these boxes are kind of just showing here. We could do the Linux x86 target as well. So we take a look at the Bamboo and Assist virtual machines a little bit. This block diagram here really just shows the Atlassian Bamboo product. And if you go down, you see the plugins that we developed. You see the CFS software. You see QEMU. And ultimately, you go down here to a tap device and IP address. This is connected via a host-only Ethernet network to the Assist virtual machine, which is your ground station software. And this wrapper application mentioned here is what will start Assist, start it executing, start running the tests, and process the results. This flow chart shows you the steps, automated steps that our system does. Mostly on the left, these steps, source code checkout, make any configuration changes you have to, build the software, and then configure Assist and start Assist. All of that really falls under building the flight software. Anything that your software under test needs to happen falls under that left side of building it, and that's what these steps here are. When we get down here to the bottom, we start Assist, we build the Assist test procedures. Once those get built, we stop Assist, and we restart it. Now we're ready to run our automated tests. Now, let me mention that all of these steps are completely automated. None of this is manual. The Linux box, this is just where you run for multiple targets. Are we running on Linux? No. Well, run your CFS core on QEMU RAD 750. If you're running on Linux, then just run on your x86 Linux. As an output of this, you have your ground test procs and post-test commands. Those get executed, and when finished, you stop. everything, you log your test results, and you identified what failed. So the point of this is that everything in this chart is automated. This is designed for one-click go, come back the next morning, look at your results, and see what you have. This way allows you to pull in, if there's a new version of CFS, you just drop it in, you run the same, hit go, run the same tests, and you look at your results.
But this will be an iteration, right? If the build fails, you're going to go back to the source code.
Yes, I mean, if the build fails, then we have to take a look at it to see why. Yes. Yeah, this assumes that it all builds. Yeah. Just these screen snapshots just show on the left. If you've never seen Bamboo, it is a web-based interface for a build server. These steps here are the steps I just described as being shown here. On the right, this is the start of assist. On the next slide, it shows it a little better. This is assist ground station starting, executing the test. So you could actually sit here, and if you're in front of it, you could actually watch it going through the procedures, executing the test. So some of the benefits and the next steps for this is, the benefits of this system was to quickly perform a checkout of CFE and CFS and execute the integration and regression test automatically. That's our biggest focus, is doing this in an automated way. Second is we want to support multiple targets, and that's where we've been going on a lot of things, is we really want to run on multiple targets. We have a lot of experience with the RAS 750. A lot of missions use it, so we really want to do some testing with the RAS 750. And we're always interested in automation of ground station software. Typically, we don't see a lot of automation of the ground station software. And when I say automation, I mean full-up automation from starting it to stopping it, and everything else in between. We don't usually see a lot of that. That's one of the things that we really focus on. So the next steps from this are to apply the lessons learned for this project and technology developed from the pilot and apply it to another NASA mission with increased focus on the IVMV life cycle. I talked a little bit about that before. So instead of CFE, maybe we have Project X, we have new flight software, we drop it in, run our test, we have results. Now we want to compare that with a previous version of flight software, run the same test again, and you have your results. The whole purpose here is to support the IVMV program to help them do their independent testing. Static analysis could also be added to this workflow in an automated way, to where it's just another output of your test and the static analysis. IVMV does static analysis now. This could be just rolled into our workflow. So with that, are there any questions?
Hold on. We got to record this. Amazing.
Are you plan to expand your target to like a Leon 3 processor?
I think the next step for us would be Leon 3, because we already have it working under QEMU.
To use a Leon processor quite a bit.
Yeah, we're aware of other missions using Leon 3, so I think that'd be the next step for us.
So if I get this, SIL, this is pretty much you're trying to virtualize the hardware, so it's more like a virtual sim, right?
Yes.
So in that regard, what I'm not seeing in your architecture diagram is, what about dynamic models? You know, every spacecraft uses different actuator sensors and all that. Do you model those?
What we typically do for those,
Okay.
The projects usually already have those models. We grab them and integrate them into our system.
Okay.
We don't typically build those ourselves.
Right.
That's where we do the COTS and GOTS integration I mentioned.
Right.
We just integrate those.
Integrate them from specific program.
Yes, from the specific.
Right.
Now, often those are hardware-based.
Yes.
And we have to virtualize that and make it software only, but we're pretty successful with that.
So then, do you have a metrics or have some sort of proven records to say your virtual sim is as good as hardware sim?
What we do is we have a specific test cases that we run, and we make sure we get the same results as the project does when they run their tests. That's how we do our validation on our simulators.
Just one more. You're running the executable image. Why not? Would you be able to get the source code and compile it and run it?
We could. We just try not to do that for purity. We like to say that we
Unmodified.
since that is the software under test, we don't want to be touching it, and we don't want anyone to say we're touching it.
So you're able, though?
We can build it if we needed to, but we like to just say we get it, and here it is running as it will in the spacecraft.
All right. Thank you.
Other questions? Okay, we're going to go that way. So,
So I had a question, but it has been already asked, so that's good. I have a comment regarding the QMU for Leon 3. So at the European Space Agency, we developed actually a product out of QMU to simulate Leon 2 and Leon 3, which is called Quarks, and it is maintained by SciSys in UK. So maybe, I don't know which person in ESA you were in contact with.
I have attended a presentation on Quarks.
Okay.
I'm somewhat familiar with it.
Okay.
And then I believe Sebastian Huber was the one who sent us these Leon 3 patches.
Okay, but I think that if you plan to start using the Leon 3 in your facility, I would suggest to get in touch with SciSys, because they have already, it has also characterized against hardware, so it is a fairly mature product in this sense. So
Okay.
it's,
Thank you for that.
better
Okay.
to start from there.
Okay.
go down here and work our way back.
I have a question. You mentioned you use QMU and CIMIX.
Mm-hmm.
Is there, what is like the trade, when would you use CIMIX and when would you use QMU? And
The first one is QEMU is open source, so it is free. I mean, there is licensing costs when purchasing CIMIX. That's probably your biggest.
do they do a similar job or?
They do. CIMIX is more geared toward modeling. CIMIX does give you a very nice tool set and framework to do your modeling that you do not have in QEMU. So that is one positive for CIMIX.
And the other question was about performance. Have you run into any issues with not being able to run as, keep up with wall clock time running these emulators, or?
We have. We have actually spent a considerable amount of time tweaking performance on our simulators. We have to work hard to get real-time performance, particularly when using CIMIX, and there's a lot of tricks that we now understand to do it.
Okay.
Yeah,
Thank you.
I could talk more about that some if you're interested in that.
Within your instruction set simulators and also the simulators for specific hardware, do you also model the execution time or just the semantics?
We really just model the semantics. But I will say for execution time, it is all discrete virtual time. So when the spacecraft, when 1 second passed on the spacecraft, it thinks 1 second passed of virtual time. Whether that took 5 seconds on wall clock time, it doesn't matter, if that answers your question.
Yes, I was more concerned with some sort of hardware which takes some time for a certain action. So you write a register, for instance, and after, let's say, 5 clock cycles, not before 5 clock cycles, you should read back a result from that hardware. If that execution time is not modeled correctly, maybe, yes, but then maybe the software works flawlessly, but on your simulator, but would fail completely on real hardware.
So we handle that by having a time master, and it's synchronous. So time will proceed forward for everyone and only everyone, and then once everyone gets the tick, then time will proceed again. So that's how that is modeled. CIMIX is the time master and QEMU is the time master. They are the clock. Their clock is what the hardware sees. If 5 microseconds on their clock takes 20 on wall clock time, it makes no difference. All of the modeled hardware sees 5 microseconds.
Other questions?
So first, just a statement. At Orbital, we actually developed a very similar simulator to this, and it's very powerful not only for the reasons you mentioned, but also for development of software. We use it as a good test bed. And similar to the question that he had asked about models, and maybe this falls in the same category, but you talked about the processor board like the RAD 750, and you talked about dynamic models of the system. But typical CNDH architecture is a box full of cards. Are you developing those models for those cards yourself in SIMX or QEMU, or is that part of your PC-based simulation environment?
We model those ourselves. The ITC team will model the specific cards for a mission in SIMX or QEMU. We have most of the experience in SIMX. An example is a KA band card with various FPGAs. We'll model that in SIMX ourselves.
So that I understand you've done that for CFE or CFS. What would you recommend for a NASA mission where you have your bus is coming from a customer and maybe it's not well documented hardware? Is it how are you planning to develop those models?
That is a challenge that we face every day, to be honest with you.
We do.
And we've done it for, CFE was the topic of this, but it's also we did it for the other missions I mentioned, JBST and GPM. It takes some reverse engineering effort. It takes looking at the documentation. And sometimes we've got to peek under the hood at the flight software to see how the flight software is using that hardware. We don't like to do that because who says the flight software is using the hardware the right way?
It's cheating, right?
But we kind of got to, being IV&V, we're somewhat at a disadvantage, and we kind of just have to do what we have to do to get it modeled.
So what I would assert, this is not part of the IV&V. I hope they're not going to use this as a part of the FPT platform, right? I mean, they have to qualify on the hardware, the platform they're going to fly on.
True.
Right. I'm not talking so much about qualification, but IB&B.
Right. So, I mean, cell is a version very close to actual hardware, but all this timing and all those models, it depends on how the fidelity of the models and
Sure.
depend, yeah.
Okay, any other questions?
Alan, I think we're over time.
We are. Okay, so thank you.
Thank you.